It's going to start streaming soon. It says start streaming. Is it coming up? There it is, starting. See? Okay. (8.1) plus 8.2 together in one, and I will say sequences and series. So I'm changing the titles a little bit. These two sections are together because some of the important information in both, but they are really should be one section. We are dealing with the basic definitions for both of these concepts, and then we are trying to understand what they are and how they work. So this is going to be that part that you are not used to, because this is now discrete mathematics. So far, you dealt with continuous, with analog functions, which means that there was a continuous stream between 2 points. If we have discontinuities, it's okay. We still have a continuity between parts. So now I'm going to compare two things. I'm going to compare y equal 1 over x, and I'm going to compare an equals to 1 over n. So you are used to y equals 1 over x. You know how that looks like. Looks like this. Where the other guy is actually not going to have anything on the other side. It's just going to have this. The difference between the two. So we are taking care of this world in this chapter, plus more, obviously. So what is a sequence? A sequence is an ordered list of numbers. And I am going to underline the word ordered. It is ordered through set of natural numbers. I'll put counting. So that means that the sequence, whose notation is an, can be a1, a2, a3, a4, dot, 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 an minus 1, an, dot, 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 going on forever. The ordering is done through this set 1, 2, 3, 4, 5, 6, 7, which is what we get as the counter. So what we are going to do now is we are going to take a look at few sequences and understand how they work. So let's say I have an is equal to 3n minus 1. So this is our sequence. What are the terms of this sequence? Well, the terms of this sequence are going to be when n, so when n is equal to 1, we have 3 minus 1, which is 2. The next number, the next natural number after 1 is 2. So 3 times 2 is 6, minus 1 is 5. 3 times 3 is 9, minus 1 is 8. 3 times 4 is 12, minus 1 is 11. 3 times 5 is 15, minus 1 is 14. And you quickly pick up the pattern that you are actually adding 3 to each one of these as you go on. We are using set notation, because this is the set of all the numbers. And as you can see, this is ordered set, not just because it goes from lowest number to highest or highest to lowest. It is ordered because we obtain these values by plugging in 1, then plugging in 2, then plugging in 3 into the equation provided to generate the list. So you can come up with whatever kind of list you want, any kind of formula to generate these terms. So let's go with Bn to be a bit spicier. So let's take a look at 2n squared divided by n minus 1. And it's not hard, it's just a little bit more annoying to compute. So we still have our input values to start at 1. So that's going to be, can't start at 1 because the denominator would be 0, right? So we have to start at n equals to 2. So this is for n larger or equal than 2. So start at 2, that's 8 over 1, so 8 is the first term. Then n equals to 3, that's 9 times 2 is 18, divided by 2 is 9. Then 4 is 16, 32 minus 32 over 3. So 2, 3, 4, 5, 25, 50 over 4. 50 over 4 is 25 halves. And let's do 6. 36, 72 over 5. And it's going to go forever. I get tired calculating these. It doesn't matter. So there they are. There they are. So we have this. It is ordered list of numbers because ordering is done by computing these formulas you get through using numbers n equals 1, n equals 2, n equals 3, so which is counting numbers, natural numbers. Can you start at 0? Yes, you can. Do we use negative numbers? No, because you will not count negative 1, negative 2, negative 3. So we can start at 0 if we need to, but generally we start at 1. Okay, now there are certain things. So let's see. These are known as explicit formulas because explicit formulas you can compute. We also have recursive ones where the next term depends on a previous term or few previous terms. Like, you know Fibonacci sequence? Fibonacci sequence takes the first two numbers and adds them to get the next number. So it starts 1, 1, and the next number is 2. And then what's the next number? Because 2 plus 1, right? So Fibonacci sequence, there's too many B's and C's in Fibonacci sequence, is 1, 1, and then 1 plus 1 is 2, and then 1 plus 2 is 3, and then 2 plus 3 is 5, and then 3 plus 5 is 8, and then 5 plus 3 is 13, and then 21, and then 34, and then you go forever, right? Now, Fibonacci sequence, how does this work? If the first term is A1, and the second term is A2, and this one is A3, and this one is A4, you can see that adding, if you call this term AN, then the next term has to be AN plus 1, which will give you the next term, which is AN plus 2. And if you look at this formula, it works no matter where you are in the sequence. So let's go all the way to, let's say, A8. If this term over here is A8, then this one must be A7, and this one might be A6, which is okay, because if the first one is 6, then the next one is n plus 1 is 7, and the next one is n plus 2, which is 8. It works. Is anyone recognizing computer science right there? Programming and algorithms. That's going to be crucial. This is the section where the Calc 2 is required for computer science. this. And then after this, you take linear algebra and discrete math. Those are the 2 courses that you actually benefit from for computer science. This is stuff you need. All right. So we can have many of these recursive ones that you can come up with whatever formula. So let's say that an depends on the term that was 2 terms prior, and then you have to add 7 to it. You can come up with whatever the hell you want, all right? So how would this work? Well, I provide you that a1, which is the first term, is equal to let's say 6. I provide you with a2 that it's equal to 12. And then you should be able to pick up from there. Let's see how this works. So if I have my sequence now, it starts at, well, I gave you the 6 and 12. Those are the first 2. And now what you do? The an, you have to go 2. So now you're here, right? This is the next one. So you have to go 2 terms before, which is 6, and add 7 to it. So this is 13. So for this position, you have to go 2 terms before, which is 12, plus 7 is 19. For this position, you have to go 2 terms before, which is 13, plus 7 is 20. For this position, you have to go 2 terms before, which is 19, plus 7 is 26. And you can go forever from there. That's how they work. Because if this is the an, which you want to compute, this term is an minus 1, which is the prior term, and this is an minus 2, which is 2 terms ago. It's just trying to find the location where you are. The ordering has to be 1, 2, 3, 4, 5 because the terms are discrete, they exist, and they're consecutive. So it's 1, 2, 3, 4, 5. If you call any term in a sequence, I'll write this in red. If you pinpoint any term as an, the next term must be an plus 1, and the term before must be an minus 1, because it's the first term before an and the first term after an. So just chasing these locations, and that's all done through ordering. Right? 1, 2, 3, 4, 5, and so on. So that's what we have. That's what we have for these. Now there are some. So these are recurrence relations and so on. And now the question is, what do we do with this? Well, the sequence could go somewhere in terms of convergence, or it could, what we say, blow up, which is divergence. You can use any, I will put in air quotation marks, function from before, replace x with n, and try to see what's happening with the sequence. Now remember, the function is continuous, right? So every point is there, where the discrete ones picks only the point above 1, point above 2, point above 3, and so on. So let's see if I take a look at, let's say, an is equal to 2n. How does the graph for this sequence look like? Well, remember, the input is always counting numbers, which means your input is 1, 2, 3, 4, 5, 6, 7, and so on. And the output is actually what you get when you find the sequence. The sequence itself is the output. So you will put ANs on this axis, and the N, which is the counting, is input because ordering is done through N. So now, 2, 4, 6, and then we run out of the room right fast after that. It's going to be 8 right there, and so on. You don't get to connect these points because there is nothing in between 1 and 2. There is no 1.3. and 1.7. Those are not discrete values. 1, 2, 3, 4, 5. So this is the graph. Now you look at the trend of that graph, and you need to answer the question: does this particular graph, these dots, does it converge to a value or diverge? Which means goes forever, grows without a bound. And the answer is grows without a bound, which means diverge. Now I can do the test for that, which we are going to define pretty soon. And the test says that the limit of an as you let n to go to infinity is going to be, in this case, limit of 2n as n goes to infinity, and we do get infinity, which is divergence. So I didn't really have to do the graph because I can only take the limit. And you know what the test says? If the limit converges, the sequence converges. If the limit diverges to infinity, the sequence diverges. Yeah, to infinity. So let's take a look at another example. Let's say you have an is 1 over n. Well, we immediately test that with the limit. N goes to infinity of 1 over n, and the answer is 0. Converges. Converges to 0. Now, if you are to try this on the graph, but clearly you're going to get that. One, 2, 3, 4, 5. These are my n's. I'm going to take this to be my 1 unit. So what is my sequence look like? If I have at 1, it's 1 over 1, it's here. For 2, is at half. For 3, is at 1/3. For 4, is at quarter. For 5 is 0.2, which is 1/5. Do we see how it's slowly going into the n axis, right? So it converges to 0. It's finite. So we saw now that 2n diverges, and we saw that 1 over n converges. As long as you know how to take the limit, have no issues in figuring out whether the sequence converges or diverges. And that is the only test that you have for sequences. So we can quickly find what is happening with every sequence. I see a very interesting sequence that they want to test in a textbook. So let's take a look. It looks really spicy. So let's take a look at that one. It says that the sequence an is given as -1 to the n divided by n squared plus 1. Good. Now, what is this -1 to the n term? What would that do? You are not clear about that. We can try and graph it. Very good. That is going to alternate our terms between on the other side of the x-axis. So let's write out this as a sequence. For n equals to 1, the top is going to be -1 and the bottom is going to be 2. Do we all agree on that when n is equal to 1? We do, right? How about n is equal to 2? One over 5. Very good. 2 squared is 4 plus 1 is 5, and -1 squared is +1. So how about the next term? -1 over 10. Very good. Next one? 17. Now I hope you guys are picking up that the negative sign goes negative, positive, negative, positive, negative, positive. It's going to do that forever because even and odd numbers always alternate. So now that creates the graph. I'm just going to do a rough sketch here because I'm not going to bother with over 10 and 17 and so on. The first term was negative, so it's going to go there. The next term goes there. The next term goes there. The next term goes there. So they jump. But you see that they're trying to settle around axis end. So just by observing that pattern there, you know that it's convergent to 0. But let's calculate that, right? Let's calculate that through our limit procedure. Limit n goes to infinity of -1 to the n divided by n squared plus 1. What happens when you have infinity for n? What happens? Why does it go to 0? We do have -1 raised to infinity. Would that contribute in any way? What's happening with, well, yeah, n squared is high, I like that. But can anyone elaborate a little bit on -1 to infinity? No, it's not canceling out. We'll address that a little bit later. Because it's 1, right? It doesn't matter how many times you raise 1. It's always 1 times 1 times 1 times 1 times 1. So the value up there can be either +1 or -1. It has to be one of those two numbers. When you divide that by infinity, you're going to get 0 either way. Fair? So it is 0. And we say converges to 0. And we have that convergence. Have another 15 minutes for this. Okay, great. So that's what we have. Converges to 0. Kind of looks scary a little bit in the beginning, right, when you see the problem. But as you can see, you can quickly take care of it. How about this one? Let's say an is equal to 5n to the 4 divided by n to the 4 minus n squared plus 1. Anyone remembers how to do the limits from Calc 1? So is this convergent or divergent? Converges at 1. Divide everything by highest power, which is n to the 4. Just 5. All of these guys go to 0 because it's n squared divided, right? So you get 1 over n squared, which is 1 over infinity, which is 0. So it's 5. You divide each one by the highest. That was the method to solve these from calculus 1. Now you can always use L'Hopital's rule. You can use L'Hopital's rule if you want to, because you do have infinity over infinity case, and you can take derivatives and you will get the same thing. Actually, yes, for polynomials. Yeah. For the other ones, you have to look at the growth rate of functions. So that's for this one. You can guys use L'Hopital's rule. I mean, everything that you learned prior to this point is okay. It's fair game. So whatever. If you remember it as the horizontal asymptote stuff from pre-calculus, you can use that. You can do the divide by highest exponent, or you can use the L'Hopital's rule, or whatever works. All right. Now, so how about this one? So let's say an is equal to e to the 5n divided by n to 100 minus 1. How about this one? What happened? What do you mean it's 1 over infinity? Let's write it out. Limit n goes to infinity e to the 5, oops, e to the 5n over n to 100 minus 1. Nope. How are your limits? Let's see who remembers the rule from Calc 1. Aha. So exponential function grows much faster than polynomial function. Okay, I like that. So what's the answer? 0. We have a faster growing function divided by the slower growing function, which means the answer is infinity, which means diverges. So this one is infinity, so we have divergence. And we will define soon faster function over slower function is infinity, slower function divided by the faster function is 0, which means converges to 0. But it can converge at any other number, right? We had one converging to 5. There's going to be a lot of cool stuff coming up in these sections. And okay, so sequences, series I'm going to leave for later. So I'll come back to sequences now. I just want to get over with the terminology for sequences. Technically, guys, what you need to learn is this chart. This is mostly for terminology. I'm thinking this is one of the pages in the book. Page 608. Looking at this chart, it gives you terminology for sequences that you should know. It says that sequence is increasing if every next term is bigger than the previous term, right? Now, but there is also a non-decreasing. So increasing and non-decreasing is not the same. There is a subtle difference between them, and you have to capture that one. So be careful. And you have examples, the good examples provided. So increasing function is 1, 2, 3, 4, 5, 6, 7. And then non-decreasing is 1, 1, 2, 2, 3, 3, 4, 4, right? So it's not increasing because 1 and 1, that's not increase there. It's constant. And then from 1 to 2 is increase, but the 1, 1 already messed it up. So yeah. And then we have decreasing, which is obviously, as you can see, 2, 1, 0, negative 1, negative 2, negative 3. So, okay. And then we have non-increasing as well. And we have monotonic and bound. Those are important, right? So monotonic moves in one. So if it's either non-increasing or non-decreasing, then it's monotonic. And then the bounded functions are the ones that do not cross certain values. So for instance, this particular function is unbounded, but the 5 is bounded, right? Because the function is bounded from that side. 1 from 0. This one bounded. Gotta switch to tablet. I gotta do these things. So let's go here. The first example, 2n. Is it bounded? No, because it's gonna go forever up, right? It's divergent. Immediately if it's divergent, it's bounded, right? How about this one? Is it bounded? Yes, it is. It's bounded, right? It's bounded from below with 0. Bounded? Yep. The highest value you can get over here is this value, which is negative 1/2. And the highest value this way is 1/5. It's bounded between these two values. You have a lower bound and the upper bound. Bounded. Obviously, if it converges, it's bounded, at least on that side. This one bounded? Nope, it blows up, right? Goes to infinity, not bounded. So terminology, please observe the theorem, the definition, sorry, the words, and so that we can communicate during the class, right? So when I say non-increasing, you know exactly what it means. There are no surprises. And they also give you wonderful examples. You just chase these dots and you know the differences between monotonic, bounded, non-bounded. And what else do we need to talk about? Geometric sequences. Well, we'll deal with this stuff with geometric series. So I'm just gonna skip over that particular concept here and jump into the squeeze theorem for sequences. So I hope you guys remember the squeeze theorem for limits from Calc 1, or you at least remember that it exists. So now the squeeze theorem for sequences is the same thing. If you have two sequences and one of those sequences and a third sequence is in between them, so whatever the other two do, the third one will do the same thing, which means if it's squeezed from two sides and two sequences are convergent, then the one that is squeezed in between has to be convergent as well. Technically, translation from what we have for our squeeze theorem for limits. So let's write this theorem for squeeze for sequences. So let the sequence AN, BN, and CN be sequences with, now this is an important statement, AN less than equal to BN less than equal than CN. So we see that the CN is above the BN and above the AN for all integers. So I just say for all n elements the counting, right? So that's for all values. If the limit as n goes to infinity, which is our test, AN is equal to the limit at the Cn, then, and that's finite, then the limit goes to infinity for Bn, which is squeezed in between, is also equal to L, which means converges to the same value. How does this look on a graph? So let's pick some values and call this one to match over here. Call this one Cn. And then we'll pick another one and call this one AN. So you see, they are pushing together to converge to a same value. Now, they don't have to be the same sequences or anything like that. They are, I mean, collective or something. The important thing is that this sequence in between that can be all chaotic and we are not good to find the limit for it or whatever. It has to stay in between and it will. Right? So if we get to wedge in another sequence in between, the limit for that sequence would be the same eventually as the other ones. So that's the squeeze theorem. And why is it squeezed? Because the red sequence, which is our Bn, is sandwiched in between. Some books call it a sandwich theorem as well. So that's that part. A bounded monotonic sequence has to converge. That should be common sense. It's a big theorem as well. Yeah. So bound and monotonic sequence converges. It's bounded immediately means it converges on that side, right? Monotonic means it's increasing. So think about this, right? Here's the bound. So it's approaching that bound, and the bound is the limit at which it converges. Converges at that value, the value of the bound. You can have the one for decreasing as well. It converges at that value. And finally, we get to define the growth rate, and that takes care of sequences. Now, this is very important because as soon as you see different functions mixed into your limits, you can invoke this theorem and quickly claim convergent, divergent, or whatever. So I'm just going to write that we are looking at the limit as n goes to infinity of sequence an divided by the sequence bn. And that could work out to be 0 or infinity. If you are using, the only way to get the actual number 5 or whatever like that is if the an and bn are the functions of the same order. And we'll have a whole spiel on that later. Right now we are looking into that the sequence ln raised to any exponent is going to be smaller than any polynomial which is smaller to any polynomial times any ln, which is smaller to multiplication of any two polynomials, which we know that we can just write as the addition of exponents, which is smaller than any type of the exponential. And now here the new one, which you haven't had so far, which is smaller than any kind of factorial, and then the boss is n to the n, the largest growth. The q, that's the exponent q. So n to the p. Just to illustrate this a little bit and show why is this so, you know from figure of speech that if something grows exponentially, it grows very fast, right? Well, look, the exponential is that b to the n. And then we still have two that are growing faster than them. The factorial one, which you haven't seen so far in your continuous math because it has no, that's a discrete function. And then you have n to the n. Well, this one you could have seen like x to the x or something. So what do we have here? We have, so I want to draw this chart, so just so we can quickly see how these growth rates work, looking at numbers. So let's have n, and then 2n, and then n squared, and then 2 to the n, and then n factorial, and then n to the n. And we start with 1, 2, 3, 4, 5, 6. Let's go up to 6, see how it goes. So the first order of business is this linear growth when the slope is 2. So we just double each one. So 2, 4, 6, 8, 10, 12. So we see that 2n beats n at any point. And then n squared, which means you take all the n's and you square them. So you get 1, 4, 9, 16, 25, and 36. So now you see that the function n squared grows faster than both 2n and n itself. Now 2 to the n. So that's 2. And then 2 to the square is 4. And then is 8. And then it's 16. So see, it's kind of losing a little bit, or it's the same as n squared. And then 16, 16. And then finally 32, 64. And then it takes off. And you can see how much 64 is beating 36, and it's beating 12, and it's beating 6. So it's really picking up there and goes on. Now, what is a factorial? Yes. Yes. Factorials multiply 1 times 2 times 3 times 4 times ... until you get to that n value. So 1 factorial is clearly 1 because it's just number. But then 2 factorial is 1 times 2, which is 2. That one is losing, right? And then you have 1 times 2 times 3, which is 6. Awful, it's losing, right? And then you have 1 times 2 times 3 times 4 is 24. All right, it's winning now, right? And then 5 factorial is 120. And then 6 factorial is 720. And you get the idea of how fast that grows from that point on, right? The next number is 1400 something. So it really grows fast. It takes some time to pick up, just a few terms. And then we have the boss, n to the n. 1 to the 1 is 1, 2 squared is 4, 3 cubed is 27, 4 to the 4 is 16 squared, which is 256 on the fourth term. Now look how much that one is winning on the fourth term. What's 5? What's 5 to the 5? 5 to the 5 is a lot, yes, because it's 25 squared, which is 625 times 5. That's 30,000, right? No, 3,000 something. 3,125, right? And then 6 to the 6 is really exploding, right? Because 6 to the 6 is going to be 36 cubed. Right? 36 cubed is 46,400, 656, 4656. You see how fast that one grows, right? So now when you see this growth rate of functions, you just take those and there we have it. Yes. This thing. So now what this means is that any time when you have, let's say, factorial divided by polynomial, it's immediately infinity. Because factorial is faster, it's on top, you're dividing faster by slower, it has to be infinity. If you have polynomial on top and the factorial on the bottom, it's 0. Because the one that is on the bottom goes faster to infinity than one on the top. And you can use L'Hopital's rule to check these at any point in time. So that's the growth rate of functions. And that concludes the sequences. So let's just wrap up that, and then we're going to define series. And the rest, the next 4 sections of chapter 8 is going to be only dealing with series. because that is what we actually are looking for. For sequences, you don't have, I mean, obviously computer science has a lot of application there, but it's actually series that we need for engineering and stuff going down the line. So what is a sequence? A sequence is ordered list of numbers. The ordering is done through set of natural counting numbers, 1, 2, 3, 4, 5. If you want to start at 0, you can. No negative values there. The graph is always, your x-axis is actually the n-axis. We only have dots, right, discrete values. And what else? We have the words increasing, non-decreasing, decreasing, non-increasing, monotonic and bounded. The only test that we have to check if these sequences are converging or diverging is limit n goes to infinity, whose answer could be either a finite value, like we had 0 and 5, or it could be an infinity, which means it diverges. Diverges means grows without a bound. And then at the end, we just, for easier computation, we look at the theorem here, which says that we can look at the growth rate of function, and then decide what the limit is going to do. The second part of this lecture is just for us to define series. And the series is going to be the sum of the sequence. So we define series. So series is a sum of the sequence. So if you guys have, let's say, an given as 1, 2, 3, 4, 5, going on forever, then your series an is actually 1 plus 2 plus 3 plus 4 plus 5 plus going forever. Now, it doesn't take a genius to figure out that this one will actually diverge because you keep adding numbers forever and the sum grows. So this particular series diverges. Now, what's important here is to understand that we started this series at 1, and then we are going to infinity. Series can be finite, always converge, or infinite, which could converge or diverge depending on what we have. We only study infinite series because finite series, who cares? Finite series always converges because you add 10 numbers and that's it. So finite series that has finite number of terms must converge at all times, because as soon as you add, I don't care whether you have 5 terms or 10,000 terms, as soon as you add them, the number that you have is the sum of the sequence, the sum of the sequence, which is the series, and it converged. But the infinite one that will have infinitely many terms, they could either converge or diverge, and that is what we are devoting the second part of this chapter, sections 8.3, 8.4, 8.5, and 8.6, to take a look at 9 or 10 different tests that will help us test this, because obviously you cannot sit there and add all of these terms up to infinity, because not else forever. So you can't be adding these forever. We're going to figure out what we're going to do with those terms. So that's all that I wanted to say for series, really, right now, because series is some of the sequence where in that term we're going to replace commas with addition, and then we're going to spend the rest of the chapter looking into. So that concludes the sections 1 and 2. And then on Thursday we're going to resume with day 3, and then we'll see what else we can do. So I'll see you then. And